In previous video, we have talked about the concept of grammar. There are three categories of grammar that we will talk about in this class. The first is simple grammar. There are two conditions to check whether a particular grammar is considered simple or not. The first condition is every rule must be of this form. On the left-hand side of the derivation arrow, it must be a single non-terminal. And then on the right-hand side of the derivation arrow, it must begins with any terminal and it can be followed by any string of terminal and non-terminal. While the second condition is, if we have more than one rules derived from the same non-terminal, the terminal on the right-hand side of the arrow must be different. Now, let's take a look at the three examples of grammar in the slide. Grammar 9, Grammar 10, and Grammar 11. Based on our understanding of the two conditions, to check for simple grammar, which of the three grammars do you think is a simple grammar? The answer is Grammar 9. Why? Because Grammar 10 has an epsilon rule, and for Grammar 11, if you see both Rule 1 and Rule 2, they begin with the same non-terminal S, and after the derivation arrow, they also begins with the same terminal A, while it is different with Grammar 9. Even though both Rule 1 and Rule 2 starts with non-terminal S on the left-hand side, after the arrow on the right-hand side, they have different terminals. Rule 1 has A and Rule 2 has B. That's why, from the three examples, only Grammar 9 is considered as a simple grammar. We know that a grammar can have many rules. When doing syntax analysis, the parsing algorithm must be able to decide which rule in the grammar to be applied. A key component is the selection set. Selection set is defined as a set of input symbols which imply the application of a grammar rule. For simple grammar, selection set of each rule is exactly one terminal, and it is the terminal on the right-hand side of the derivation arrow. Let's look at Grammar 9. This is the derivation arrow, and the terminal on the right-hand side is the selection set for each rule. So if you look at Grammar 9, the selection set for Grammar 9 is this. For Rule 1, it is A, and for Rule 2, it is B, because these are the terminals that begins immediately after the derivation arrow. Now, how about Grammar 11? If you look at Grammar 11, the selection set for Rule 1 is A, and the selection set for Rule 2 is also A. They have the same selection set for the same non-terminal S. Therefore, Grammar 11 cannot be used in parsing algorithm because their selection sets overlap. With selection set, we know which rule to be applied when building a derivation tree. So for example, this is a string and this is the grammar. Grammar 12 is the grammar. We need to build the derivation tree for the string ABB ADDD. So we will start with our starting non-terminal. The starting non-terminal is S, and all three rules start from the same non-terminal. So we need to choose which rule to be used, whether Rule 1, Rule 2, or Rule 3. So what we're going to do is we're going to look at the current input string. We are trying to write A, and we're going to start with S. So let's draw our tree, we're going to start with S. Look at our grammar 12 and look at the selection sets for grammar 12. Which of these rules begins with A, given that A is our current input? The answer is rule 1. Therefore, when we start drawing our derivation tree, we're going to apply rule 1. So S can be derived to A, B, S, D. Now, let's look at our current derivation tree and what are the terminals that we have already included inside the tree. We have included A and also B, which means these two inputs are done, and now we're going to have to draw B under S. Now, look again at our grammar and choose the one that has B as its selection set. The answer is 2. Therefore, we're going to continue drawing our derivation tree by applying rule 2 under S over here. So it's going to be B, A, S, and D. So now inside our tree, we also have B and A. So we can cancel the two input strings here. Now, our current input would be D, and we want to draw D or write D under the non-terminal S. Going back to our grammar, we're going to have to choose the rule that has D as its selection set. The answer is rule 3. So, applying rule 3 over here, I will derive it to D. So, D is completed, and if you can notice, the remaining 2 D's is already included inside our derivation tree. Therefore, we are done drawing the derivation tree for the input string A, B, B, A, D, D, D. In previous video and tutorial, we have discussed how to use a pushdown machine to check whether a particular input string is accepted or rejected by a grammar. Now we are going to learn how to construct a pushdown machine for simple grammar. A pushdown machine is represented with a table. The column part is for terminal symbols ended with end marker, and the rows part is for all non-terminal and terminal ended with bottom marker. So now let's start by constructing a pushdown machine for grammar 13. So I'm going to start one by one. Build a table with each column labeled by terminal symbol and each row labeled by both non-terminal and terminal. So I'm going to count first. How many symbols do we have in grammar 13? So we have 1, 2, we have 2 non-terminal, and then we have 1, 2. We have 2 terminals, which means we have 4 symbols. Therefore, when we start drawing the table, we're going to need 4 rows. Okay, 2, 3, 4, and the last row would be for bottom marker. So when we are constructing our pushdown machine, it is important to start with non-terminal first, and it is important to start with starting non-terminal first. Our starting non-terminal for grammar 13 is S. Therefore, I'm going to fill up my table with S, and then the next non-terminal is B, and then we have the 2 terminals A, B, and finally ends up with bottom marker. And now for the column part would require terminals only. So we only have 2 terminals. So I'm going to just need 3 columns. 1, 2, and 3. And I'm going to fill them up with terminals A, B, and ends it with N marker. So I am done with step number 1. And now, how about step number 2? For step number 2, for each grammar rule of the from, A can be derived to A alpha, fill in the cell in row A and column A with replace alpha reverse A. So how exactly are we going to do that? So it is actually very simple. First, we need to identify what are the selection sets for each of these rules. So we have 4 rules in grammar 13. The selection set for rule 1 is A, for rule 2 is B, rule 3 is A, and rule 4 is B. I'm going to start with rule 1. So the non-terminal is S and the selection set is A, which means the place for rule 1 is here, where S overlap with A. For rule 2, the non-terminal is S and the selection set is B. So this is the place for rule 2. For rule 3, the non-terminal is capital B and the selection set is terminal A. So this is the place for rule 3. And finally, for rule 4, the non-terminal is B and the selection set is lowercase b. So this is the place for rule 4. How do we fill up the cells for these rules? So we're going to use this formula. How exactly are we going to do that? Let's start with rule 1. So for rule 1, it states that S can be derived to A as B. So we're going to take this particular portion of the rule and it's going to be replaced. And then we're going to reverse this string. Instead of lowercase a and capital SB, is going to be capital B S A followed by retain. So this is how we fulfill this particular condition. I'm going to continue with rule 2. So for rule 2, it's going to be replace B. So a single B, if you reverse it, it still is a B and not a D. Retain. Now for rule 3, a single terminal A, therefore it's going to be replace A, retain. And finally, for rule 4, the string is BBA, so it's going to be replace, we reverse the string, A, B, B, retain. So we are done with the second step. Let's continue with step number 3. It states that fill in the cell in the row A and column A with pop at fonts for each terminal symbol A. So we have 2 terminal symbols, A and also B. So for A that intersect with A, I'm going to fill it up with pop at fonts. Same goes for B intersect with B. It's going to be pop at fonts. So we are done with step number 3. Next, step number 4. Fill in the cell in the row bottom marker and column end marker with accept. So for bottom marker that meets end marker, the value should be accept. Step number 5. Fill in all other cells with reject. So we reject. all the other cells. And finally, the last step, initialize our stack with bottom marker and the starting non-terminal. So we're going to initialize our stack. So this is a stack with bottom marker and the starting non-terminal. So our starting non-terminal is S. So we are done constructing a pushdown machine for simple grammar. This is the extended pushdown machine that we have constructed using the steps in the previous slide. I'm sure you all have noticed a different operation in the pushdown machine here compared to the one we did on balance or imbalance parentheses. There is a new operation called replace. This pushdown machine is now an extended pushdown machine. And to do a replace operation, symbols on top of the stack is replaced in a LIFO manner and the current input pointer is retained. Advanced operation, meanwhile, is performed if the symbol at the top of the stack is the same as the current input pointer. And finally, when all input strings have been read and we are left with N marker, stack should only be left with bottom marker to get the string as accepted. Let's demonstrate how a string can be checked whether it is accepted or not using an extended pushdown machine. So remember, we initialize our stack with bottom marker and starting non-terminal, and I'm going to check whether this particular input string ABA is accepted or rejected by our grammar. So we're going to start with the first string, and the first string is A. So as that meets with A, it says replace B as A retain. We're going to do this operation in a LIFO manner. So how are we going to do that? S will be taken out and S is replaced with the stack symbols inside this parenthesis. So it's going to be B S A retain. Retain means we are still at the current input pointer A. Next, we're going to read symbol on top of the stack, which is A, with the current input pointer, which is still A. So A meets with A, it says pop advance. So pop advance means symbol at the very top of the stack will be popped out and input pointer is advanced to the next input, which is now B. So our current pointer now is B. Next, I will read S with B. So S with B, it says replace B retain. So we're going to take out the symbol on top of the stack and replace it with B. Now our stack is going to be B, B, retain. Next, we will read B with the current input of B. So B with B is pop advance. So we pop this string out and we advance to the next pointer. So it's going to be B. So next pointer is A. Okay, moving on, we will read B and A. B and A is this one over here. It says replace A retain. So I'm going to replace our symbol on top of the stack, which is capital B, with A and retain current pointer. So we are still at A. Next, we read A with A. So A with A is pop advance. So pop the current the symbol on top of the stack and advance to the next pointer. So we have reached the end of the input string. So at the end of the input string is supposed to be end marker. Therefore, bottom marker and end marker, and we read bottom marker, end marker, and the value is accept. So it means here the string ABA is accepted by the pushdown machine for our grammar. We now know that from a grammar, we can write a program that can accept any string in the language of that grammar and reject any string not in the language of that grammar. So there is a software that we can use to automatically generate that process, and this software is called compiler. An example of compiler is SableCC. So we have used SableCC for lexical analysis previously. SableCC can also be used for syntax analysis. Alternative of using a compiler is through a method called recursive descent. So what is a recursive descent parser? It can be defined as a parser written using a traditional programming language such as Java or C++. In order for us to do that, we're going to write several methods, and methods are written for each non-terminal in the grammar. So this method will handle non-terminal by calling the name of that non-terminal, the method for that particular non-terminal, and it handles terminal by reading another input symbol by moving on to the next pointer. Like if in a pushdown machine, if you're doing stack parsing, it is like the equivalent of a pop advanced operation. This is an example of a method, and this method is called the parse method. So this is the starting method that we will run when we want to do an input parsing using a recursive descent parser. So this parsed method is like the recursive descent parser equivalent of initializing our stack with bottom marker and the starting non-terminal, because if you see here, we also have S method. It is calling for S method, and S is our starting non-terminal. So how do we write the recursive descent parser for grammar 13? So we're going to write the methods for non-terminals, and if you still remember, we have two non-terminals in grammar 13. We have S and we also have B. Therefore, we need to write two different methods, method S and method B. Let's start with method S first. So we're going to start by defining as a void method, and there are two rules in grammar 13 derived from non-terminal S. There are rule 1 and rule 2, which means we need to include both rule 1 and rule 2 in our method S. In order for us to write the method for recursive descent parser, we still need to know what are the selection set for all the rules. So selection set for rule 1 is A, rule 2 is B, rule 3 is A, and rule 4 is B. We're going to start with rule 1 first. We need to write this particular condition. If input is equals to A, because we are trying to write the program for rule 1. So what we do is, now let's look on the right hand side of our rule. So the right hand side is ASP. The recursive descent parser, when it meets with a terminal, it will call for next input, because this is a terminal. Therefore, it will call the next input using this particular command, input equals to get input. And then after terminal A, we meet non-terminal S. So a recursive descent parser handles non-terminal by calling the method for that non-terminal. So we are going to call the method for S, and then we're going to call the method for B. So we are done with rule number 1. So moving on, let's go to rule number 2. For rule number 2, the selection set is B. So we're going to start else if input equals to B, and then on the right hand side of rule 2 is a single terminal B. So recursive descent parser handles terminal by calling for next input. Input equals to get input. So there are no other rules in grammar 13 that are derived from non-terminal S. Therefore, if the current input is not A or not B, we want to reject. So we add the final condition, else reject, and close the curly braces. So we are done with the method for non-terminal S. Okay, moving on, let's write the method for non-terminal B. So I'm going to start by declaring a void method B, open curly braces. There are two rules derived from non-terminal B, rule 3 and rule 4, and the selection set for rule 3 is A. So I'm going to check if the current input is A. If input equals to A, so what we need to do is look on the right hand side, and it is a single terminal. The recursive descent parser handles terminal by calling the next input. So it's going to be input equals to get input, else if. Okay, so we are done with rule 3. Now moving on to rule 4. Else if input equals to B, because B is the selection set for rule 4. Look on the right hand side of the rule, it starts with terminal B. And remember, to handle that, we're going to call next input. So after B is a non-terminal B, a capital B. So we do that, we handle that by calling the method. And then after B, so pay attention here class, is a terminal A. What we need to do here is we need to check whether the current input pointer is A. So we do another checking. There is a nested checking here. If input equals to A, what we do is we move to next pointer. However, if the current input is not A, we need to reject it. Okay, so we are done with this. So we are done with rule number 4. So we close the curly braces for rule number 4. And we are finished with the rules that are derived from B. Rule 3 and rule 4. But what if the current pointer is not A and or is not B? So we need to reject. So at the last condition, we add else reject, and we close the leftmost curly braces. And these are the two methods that we have written for grammar 13, and these two methods are part of the recursive descent parser for grammar 13, which is another way of parsing input in addition to pushdown machine.